There is a star in our galaxy that astronomers have been quietly watching for years, not because it suddenly flared up, but because it refuses to behave normally. Its light rises and falls on strange schedules, its spectrum hints at extreme temperatures, and its long-term trend suggests something is slowly being wound tighter and tighter. That star is V Sagittae. From Earth it looks unremarkable. No naked eye drama, no sudden flash lighting up the sky. But when you plot its brightness over time and compare it to other known systems, V Sagittae starts to stand out in uncomfortable ways. It does not act like a stable star settling into old age. It acts like a system under stress. Astronomers think that stress comes from an imbalance that cannot last forever. Matter is moving where it should not be. Energy is being released faster than usual. And the object at the center of it all is sitting right on the line between stability and catastrophe. What makes this case different is timing. Exploding stars are usually discovered after the fact. A telescope catches the flash, then scientists rewind the data to figure out what happened. V Sagittae is different. This is one of the rare cases where astronomers believe they are watching the lead-up in real time, seeing the warning signs before the main event. That does not mean an explosion is guaranteed tomorrow or next year. Stars do not run on human clocks. But it does mean we may be watching a system that is slowly approaching a physical limit, one that ends only one way. And that raises a rare question in astronomy. What does it look like when you catch a star before it breaks? V Sagittae is not a single star. It is a tightly bound binary system, two objects locked in orbit so close that one is actively feeding on the other. That detail changes everything. At the center of the system is a white dwarf. This is the dense, burned-out core of a star that already lived and died once. It is roughly the size of Earth but holds a mass comparable to the Sun. White dwarfs are stable only because a delicate balance of physics holds them up. Add too much mass, and that balance fails. Orbiting nearby is a companion star that is still alive. But it is losing material. Gravity from the white dwarf pulls gas off the companion's outer layers, creating a stream of matter that spirals inward. That material does not fall straight down. It forms a hot, rapidly spinning accretion disk that glows intensely as friction heats it up. This setup puts V Sagittae in a rare and extreme class of systems. Most variable stars change brightness because of pulsations or surface activity. V Sagittae changes because mass is moving, heating, and crashing into an object that has very strict limits. What makes the system especially unusual is how energetic it is. The white dwarf in V Sagittae appears to be accreting matter at an exceptionally high rate. That leads to powerful radiation, strong stellar winds, and brightness changes that do not follow the neat cycles astronomers expect. In simple terms, this is a system where the engine is running hot all the time. Nothing is settling down. And when a white dwarf is forced to keep accepting mass without relief, the question stops being if something will happen and becomes when the physics finally gives way. The danger in V Sagittae does not come from a sudden trigger. It comes from patience. The system is slowly stacking the deck against itself. As the companion star loses gas, that material piles onto the white dwarf. Every gram adds pressure. White dwarfs are supported by a quantum effect called electron degeneracy pressure, not by heat from fusion. That support works only up to a hard limit. Push beyond it, and the star cannot adjust or expand to compensate. In many similar systems, the build-up happens in bursts. Material accumulates, ignites in a surface flash, and blows off in a nova. The white dwarf loses mass, resets, and the cycle starts again. V Sagittae does not behave so cleanly. Evidence suggests that much of the incoming material is burning steadily instead of exploding right away. Hydrogen fuses into heavier elements as it lands, releasing energy but staying bound to the star. That matters because it means mass is not being shed efficiently. The white dwarf is gaining weight over time. This creates a dangerous feedback loop. More mass increases gravity. Stronger gravity pulls in material faster. Faster accretion raises temperatures even more. The system brightens, dims, then brightens again, not randomly but as part of this unstable balancing act. There is a ceiling here. Once the white dwarf approaches a critical mass, the physics changes abruptly. At that point, there is no slow adjustment left. Either the surface layers ignite catastrophically, or the entire star undergoes a runaway reaction that tears it apart. From the outside, this build-up looks quiet. No explosion yet. No obvious warning siren. But on the inside, the system is behaving like a pressure vessel with the valve partially jammed, slowly climbing toward a limit it cannot cross gently. V Sagittae has been known for more than a century, but for most of that time it was treated as a curiosity, not a ticking clock. What changed is not a single dramatic flare, but a pattern that only becomes obvious when you zoom out and look across decades. When astronomers compared long-term brightness records, they noticed that the system is not just fluctuating. Its average behavior is drifting. Periods of high luminosity are lasting longer. The dips between them are changing shape. That suggests the underlying engine is evolving, not just cycling. Spectroscopy adds another layer. The light from V Sagittae carries signatures of extremely hot gas and strong outflows. Those features imply sustained nuclear burning on the surface of the white dwarf, not brief flashes. That is unusual, and it narrows the list of possible futures. Modern instruments make this more convincing. Continuous monitoring from automated surveys now fills in gaps that used to hide slow trends. Instead of isolated data points, astronomers can see the system breathing over time, and what they see looks less like stability and more like escalation. There is also a population-level clue. Systems like V Sagittae are rare. Even rarer are ones that appear to be gaining mass rather than shedding it. That makes this object valuable because it may represent a short-lived phase that most systems pass through too quickly to catch. No one can put a date on what happens next. But the reason for the attention is simple. The data no longer fit a story where nothing important is changing. V Sagittae looks like a system moving in one direction, and astronomy does not get many chances to watch that kind of process unfold before the ending arrives. When people hear that a star might explode, they usually imagine a supernova lighting up half the sky. V Sagittae is more complicated than that, and the range of outcomes matters. The mildest possibility is a nova. In this case, the outer layer of the white dwarf ignites in a thermonuclear flash and blows off into space. The star survives. These events can be bright, but they are surface-level explosions. If V Sagittae sheds enough mass this way, it could relieve the pressure and delay anything more extreme. The more serious scenario is a Type Ia supernova. That happens if the white dwarf keeps gaining mass and approaches its critical limit. At that point, carbon fusion ignites throughout the core almost simultaneously. There is no gradual release. The star is completely destroyed in seconds. This kind of explosion would be visible across the galaxy. For a brief time, it could outshine every other star in the Milky Way combined. But it would not be dangerous to Earth. V Sagittae is far too distant for any harmful effects to reach us. Right now, astronomers lean toward caution. While the system shows worrying signs, it is not clear that it will reach the supernova threshold without first losing mass in repeated outbursts. Nature often finds ways to bleed off energy before catastrophe. What makes V Sagittae special is not certainty. It is proximity to the line. Few systems give such a clear view of the physics that decides whether a white dwarf stabilizes, erupts, or completely unravels. Whatever the outcome, the explosion or the near miss will teach astronomers how close is too close when a star starts pushing against its final limits. V Sagittae is not famous because it is exploding. It is interesting because it has not yet. Astronomy usually works in hindsight. We see the aftermath and reconstruct the cause. This system flips that around. It gives scientists a chance to watch the stress build, to track how matter moves, heats, and destabilizes a star that already sits at the edge of what physics allows. Whether V Sagittae ends in a nova, a supernova, or something in between, the real value is in the waiting. Every year of observation sharpens our understanding of how white dwarfs behave when pushed too hard for too long. These are the same objects astronomers use to measure the expansion of the universe and map cosmic distances. Getting their failure modes right matters. There is also something quietly humbling about it. The processes shaping this system unfold over timescales that ignore human urgency. Decades of data are just a blink in the life of a star. Yet within that blink, patterns emerge, limits appear, and physics stays honest. V Sagittae reminds us that the universe does not need spectacle to be dramatic. Sometimes the most important events are the ones still forming, visible only if you are patient enough to keep watching.